Mixtures of gases. A lot of gas samples are mixtures rather than a pure substance. Air is a mixture of gases. Dry air contains nitrogen, oxygen, argon, carbon dioxide, and other gases in trace amounts. Now, the air in the room might feel dry, but there's actually a bit of humidity, 36% according to the weather station. So there's a little bit of water vapor as well. So when we talk about dry air, we mean air without any water. So this is the normal composition of air. It's not something you memorize. Nitrogen, 78%, oxygen, 21%. Everything else is pretty small. Often we can think of a mixture of gases as being a single gas, because the properties of gases depend on the number of particles and not what those particles are. So air is a mixture, but we can measure the pressure, the volume, and the temperature just like it was a single gas. And we can even calculate the total moles of particles in that air sample. And this is because gases behave independently of each other. Sometimes, though, we need to know the pressure of a particular gas in the mixture. That would be called the partial pressure. So the pressure of a single gas in a mixture is a partial pressure. The sum of the partial pressures gives us the total pressure. So all the partial pressures add up to the total pressure. And that's what Dalton's law of partial pressure tells us. If we take the pressure of each individual gas and add them together, we get the total pressure of the gas. So the pressure of an individual gas in a mixture can be calculated using the ideal gas law. PV equals nRT. It's about nRT. If we want pressure, we're going to divide by volume. The pressure of an individual gas is equal to nRT over V. So P with a subscript total is the total pressure, and with a subscript A, B, C, or with an element or a compound formula, that would be the pressure of the individual components. I'm going to go through this derivation really quickly because I'm not going to test you on it, and I know a lot of you are not interested in it, but for those of you that are, the total pressure is the sum of all of the individual pressures. From the ideal gas law, the pressure of gas A is nRT over V, the number of moles of gas A. And for B, it's the number of moles of gas B times RT over V. Because these gases are in the same sample, their temperature and volume are the same. And so we could add however many there are. RT and V are the same for each of these terms, and so we can factor that out and see that the number of moles of each type of gas would give us the total number of moles of gas. So the total pressure is equal to the total number of moles of all the gases times RT over V. If we take the pressure of an individual gas and divide it by the equation for the total pressure, we can cancel out the R's and the T's and the V's, and we end up with the partial pressure over the total pressure is equal to the moles of the individual gas out of the total moles of gas. This term here is called the mole fraction. It's given the symbol chi sub A. It's the moles that you're interested in divided by the total number of moles. It's like a percentage, but without the times 100. There's a blank space here. I'm pretty sure I'm supposed to write something in there, but I'm not remembering right now what that is. Number of moles of a component in a mixture divided by the total number of moles in a mixture is the mole fraction. So that's the definition of mole fraction. So right here, this is taking this part and that part, so those are equal to each other, and then moving P total over to this side, getting that. This is chi and substituting that in, and we get this result. The partial pressure of a gas is equal to its mole fraction times the total pressure. Partial pressure of a component in a gas mixture is its mole fraction multiplied by the total pressure. Gas mixtures are often identified as volume percentages, and a mole fraction is the same as the volume percentage divided by 100. So air is 78% nitrogen. Find its partial pressure. Well, if it's 78%, that means it's 78 parts nitrogen out of 100 parts air. So we could express that as 78 moles of nitrogen per 100 moles of air, and that gives us a fraction of 0.78. Right? That's the percentage divided by 100. That is the mole fraction of nitrogen in air. So the partial pressure of nitrogen is the mole fraction times the total pressure. So the partial pressure for nitrogen is 0.78. So nitrogen makes up 78% of the particles in air. Nitrogen accounts for 78% of the pressure exerted by the whole sample. If you think about it that way, it maybe makes a little more sense. Some chemicals react with air, highly reactive, and so if they're exposed to air, they're going to undergo reactions, and you can't store them that way. So to prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. Well, what does STP tell me? STP tells me that the temperature is 273.15 Kelvin and the pressure is 1 atmosphere. And if it's helpful, I can use 22.4 liters per mole, the molar volume of a gas. Those are things, you see STP, those are pieces of information in there. It wants the partial pressure of each gas. Well, we just learned an equation expressing the partial pressure. So let's just start with helium. The partial pressure of helium is equal to the mole fraction of helium times the total pressure. What's the total pressure? 1 atmosphere. So what do I need to find? I need to find the mole fraction of helium. The mole fraction of helium is the moles of helium divided by the total number of moles. This is going to be tedious. Sorry. 5.50 grams of helium. Can we convert that to moles? Yes, we can. Divide by the molar mass. 5.5 divided by 4.003. I'm going to be sloppy here and just keep 3 sig figs. 1.37 moles of helium. And I can calculate the moles of neon. So 15 divided by 20.18, 0.743 moles of neon. And the moles of krypton, it's 131? No. 83.80. .408. Moles of krypton. You got 0.417? Yes, because I divided by 85 instead of 83. Yep, 0.4176 or 0.418. So I have the moles of each gas. To find the mole fraction, I want the moles of helium. So the mole fraction of helium is equal to the moles of helium divided by the whole thing. Moles of helium plus moles of neon plus moles of krypton. So if I add these together, this one and this one and this one, my total number of moles is 1.37 plus 0.743 plus 0.418, 2.531. So the total number of moles is the sum of the individuals. .531. So moles of helium, they look so much alike. 1.37 moles divided by 2.531 moles. Mole fraction of helium is equal to 0.541. It's unitless because moles cancel out, there's no units. So the partial pressure of helium is its mole fraction, 0.541, times the total pressure, which is exactly 1 atmosphere, and so the pressure is 0.541 atmospheres. It's tedious. How do I figure out what the other two are? Well, if I want neon instead, I'm just going to put in the moles of neon here, which was 0.743 moles. So the mole fraction of neon is 0.743 divided by 2.531. 0.294. The partial pressure is the mole fraction times the total pressure. Here the total pressure is 1 atmosphere. And so the partial pressure of neon is 0.294 times 1. 0.294 atmospheres. When I get to the last one, I have options. I can do the same process, just cross this off and put .418 in there and divide. That works perfectly fine. Actually, let's do that. I'll make that one red. Make this krypton. And that's 0.418. And so for krypton, we end up with 0.418 divided by 2.531, 0.165 times 1, 0.165 atmospheres.
So the X helium, that's referred as a refraction, the mole fraction?
Yeah, it looks like an X that's kind of curvy. It's a chi. It's a Greek.
So if we ask for the mole fraction, we just solve for the XHE helium. We don't have to like put it in like moles over total.
Well, if you want the mole fraction and you have the partial pressure, you can use this equation. If you're trying to calculate just the mole fraction of helium, then you would use this equation, the moles of helium over the total moles of gas. So here, with this third one, I can do it the same way I did the others, or I could say, well, my total pressure is 1 atmosphere. I got not much space, 1 atmosphere, and 0.54 of that is helium, and 0.294 was neon, and so the rest must be krypton. 1 minus 0.541 minus 0.294, 0.165. Yes?
So if we're giving the partial pressure of neon, for example, to
Mhm.
and we're giving the total pressure, we'll just divide the total pressure from the partial in order to get the mole fraction.
Right. Yep. Questions? Yes?
So whatever the given pressure is, it should always add up to exactly that.
Yes. Yeah. So all of the individual gases in the mixture, their partial pressures have to add up to the total pressure. Just like if you had a box of fruit that weighed 100 pounds, it'd be a big box, and it was apples and bananas and oranges, right? If you knew the mass of the apples and the bananas, you could figure out the mass of the oranges without actually weighing them, because it must be 100 pounds minus the other fruit, right? It's the same idea, but pressures. Gas mixture contains an equal number of moles of helium and neon. The total pressure is 3 atmospheres. What are the partial pressures of helium and neon? The partial pressure is related to how many moles there are, right? The number of particles. It says we have an equal number of moles of helium and neon. So that means their pressures are the same. They're equal. So we're going to choose the answer where they are equal and add up to 3. So it must be C. Your final exam from the American Chemical Society has a lot of conceptual questions. If you know your stuff, you can answer them very quickly. This doesn't involve a long, hairy calculation like we did on the last example. But we have to know what these things mean. Right? A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr. Water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? there's a lot of numbers here. So 755 torr and 24 torr, 1.55 liters, 298 Kelvin. The mixture has a total pressure of 755. So I'm going to call this P total. The water vapor has a partial pressure of 24. So 24 is the partial pressure of water. And then I've got volume and temperature. In this gas mixture, I have hydrogen and I have water. Two gases. Dalton's law of partial pressures tells me that the partial pressure of hydrogen plus the partial pressure of water must equal the total pressure. I want to know the moles of hydrogen gas. Not the moles of gas, period. I just want the hydrogen. I don't care about the water. So when I use my ideal gas law to calculate moles, I need to use the pressure of hydrogen. So I need to find the partial pressure of hydrogen. The partial pressure of the hydrogen, the thing I'm interested in, is the total pressure minus the partial pressure of the other thing in there. So 755 minus 24, 731 torr. So there's my pressure, here's my volume and my temperature. I'm going to use the ideal gas law. This isn't going to work, so I have to convert that to atmospheres. Oh, 96. 184. Atmospheres. So that's the part we just learned about. The rest of this we learned earlier this morning. Ideal gas law, PV equals nRT. Here we're trying to find the moles of gas. So we rearrange that. Moles is pressure times volume divided by R times T. Now I've got all my units, my numbers, and I can plug them in here. What did I do wrong there? I put the temperature in the numerator instead of the denominator. Fix that. That's supposed to be the volume up there. I have 0.0610 moles of hydrogen gas. Anybody else get that? Or get something different that you'd like to argue about? This number is not looking familiar to me, but I don't no reason to believe that it's wrong. Oh, there's the answer. Cool. Got it right. So we mentioned scuba diving at the beginning of the chapter, and this idea of partial pressures is very important when you are breathing mixtures of gases. A diver's breathing compressed air, so the air is at a higher pressure. This can lead to an abnormally high partial pressure of oxygen in the lungs. And so that would lead to an elevated concentration of oxygen in your tissues. You might say, well, what's wrong with that? Oxygen is good for you, right? Yeah, everything in moderation. Too much oxygen will kill you, right? Not enough oxygen will kill you. You got to find that sweet spot in the middle. Oxygen toxicity occurs above oxygen partial pressures of 1.4 atmospheres. But hypoxia, not enough oxygen starvation occurs when the pressures are too low. So that would be down at like 0.1 atmospheres of oxygen. When you breathe compressed air, you're also getting an increased partial pressure of nitrogen, which causes excess nitrogen in your tissues, and that has the effect of, is similar to alcohol intoxication. It's called nitrogen narcosis, or rapture of the deep. You might say, well, that sounds pretty fun. Yeah, but when you're drunk, maybe you don't get drunk. That's good for you. When a drunk person is making decisions, do they make good decisions? Often not, right? Their judgment is impaired. So here you are, meters and meters below the surface, breathing air out of a compressed tank, and do you want to have bad decisions? No, that could kill you. So to avoid the problems of too much oxygen and nitrogen narcosis, deep sea divers will often breathe specialized mixtures of gases. Heliox is one of them. It's a mixture of helium and oxygen. There's no nitrogen in there. You don't need the nitrogen. It's just kind of a filler gas in the air. So heliox will allow you to control the amount of oxygen that you're getting, and then you won't have any worries about the nitrogen. Of course, that would make your voice really high, but nobody can hear you when you're talking down there, so it's not really any fun. In this illustration, we see at the surface with a total pressure of 1 atmosphere, the partial pressure of nitrogen is 0.78 and of oxygen is 0.21. 30 meters below the surface, you'll have to be breathing 4 atmospheres of pressure of air, and that'll give you 3.12 atmospheres of nitrogen and 0.84 atmospheres of oxygen. Those partial pressures are too high. At a higher pressure with heliox, you can have the correct mole fraction of oxygen. So a diver breathes a heliox mixture with an oxygen mole fraction of 0.05. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? Well, let's write down what they've given us. The oxygen mole fractions, that's that chi, mole fraction of oxygen is 0.050. And the partial pressure of oxygen we want is 0.21 atmospheres. And it's saying, what's the total pressure going to be? Well, the equation that we had was that the partial pressure was equal to the mole fraction times the total pressure. So the total pressure will equal the partial pressure divided by the mole fraction. Yeah, I was blanking here. 0.21 divided by 0.050. So 4.2 atmospheres. So down around 30 meters, where you need to be breathing 4 atmospheres, this would work. What do you do in between? You have 2 tanks, one with air and one with heliox. And as you go down, you gradually switch from the air to the heliox, and so you control your oxygen intakes. One of the reasons they make you take all those lessons. Complicated, huh? Yes?
Weren't they saying breathing helium? Or is it a tank of heliox and a tank of oxygen?
Heliox is a mixture of helium and oxygen.
Okay. So you don't have 2 tanks, one with helium and one with oxygen?
No, you have 2 tanks, but one's air, and one's a mixture of helium and oxygen. Now, too much helium could kill you too, right? But the way it would kill you is that you wouldn't get any oxygen, right? So if you just breathe helium, you're going to asphyxiate because you won't get any oxygen. That's not going to happen here because there's oxygen with the helium.
Is it a myth that when they say you breathe a helium balloon, it's freezing your brain cells?
It's not freezing your brain cells. And as long as you're upright, breathing helium in is going to be fine. The problem is if you were upside down, breathing helium in, then the helium will tend to stay in your lungs because it rises, and you're going to maybe struggle for a while before you can get all the helium out. Strange fact.
Speaking of helium, why does our voice alter instead of the helium?
Why does our voice change? I think that's because of the density of helium is much less than of air, and so the vibrations of your vocal cords are going to make sound waves of a different wavelength.
So you're saying if we were upside down, helium would be in our lungs longer, so that means you would speak like that longer?
Well, you'll only speak like that as the helium's coming out. So if it's stuck there, then you could speak normally and still have helium in your lungs, I suppose.
And then an hour later it's spurred out and the voice would just go back up again.
Yeah, I mean, weird things, right? Well, that was a fun tangent. 4.2 atmospheres. One of the reasons we're concerned about this partial pressure business is because when we generate gases in the lab, we often collect them over water. So what does that mean? Well, we've got an illustration here. So here's our test tube, and we're mixing zinc in hydrochloric acid, and this reacts and gives off hydrogen gas, and we're wanting to collect the hydrogen. Gases tend to just expand to fill whatever the container, whether it's the room or the state or whatever, it just keeps expanding. So if we want to keep this, we have to capture it in a container. So we can take an inverted cylinder with water in it, starting out with no air, and make this hydrogen go through a tube and let it loose under this inverted container. The hydrogen is going to bubble up and get trapped up here, and the water level is going to go down as the hydrogen begins to fill this cylinder. As long as we control it and don't allow the helium to get larger than this container, as long as there's some water there, we can trap the helium in the container. What we have here, though, is not, helium. Hydrogen is what we're talking about, trapping the hydrogen. What we've got here is the hydrogen gas, but not just hydrogen gas, because the water is also evaporating, and so we're going to have some water vapor mixed in with our hydrogen. So if we want to know the pressure of the hydrogen, we can figure that out by the total pressure and subtract the pressure of the water. And that's a very common calculation. The partial pressure of water conveniently depends only on the temperature of the gas liquid mixture there. So if you know the temperature of the water, which is pretty easy, just stick a thermometer in it, then you can know what the vapor pressure of the water is because other people have measured it and determined it and put it into nice little tables that you can look up, right? So you can look up in the table what the partial pressure or the vapor pressure of water is, and then you just subtract that from your total. So here's an example of a table. You can get some that are much more detailed. This one goes mostly by 5-degree increments. So here's a problem using that. A sample of acetylene is collected over water. So anytime you're collecting over water, you have a mixture of the gas you're interested in and water. The total gas pressure is 738 torr and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. Excuse me. How many grams of acetylene are collected? So this is an example of a problem where we don't have to go look up the vapor pressure, they give it to us. Other times they'll just say collected over water, they'll give you the temperature and they won't say anything about the vapor pressure of water. And then a lot of students will just calculate using the total pressure and get the wrong answer. What happened? Yeah. So collecting over water, we have a mixture. So we have our acetylene and water vapor gives us our total pressure. So they gave us the total pressure, they gave us the partial pressure of water, so the partial pressure of the acetylene is the total pressure, 738 torr, minus the partial pressure, or the vapor pressure of water, 21 torr, so that's what, 717 torr? I'm suddenly writing very large, I don't know why. How many grams of acetylene? What can we find using the ideal gas law? Moles. So we can find the moles of gas, and then we're given the formula so we can calculate the mass and the molar mass. So the moles of gas is the pressure times the volume over RT. Is this pressure going to work for us? No, we need it in atmospheres. We don't need the chart for this one because they told us what the vapor pressure is. If they didn't tell us, we'd have to look this up. Yeah. So our pressure, the pressure of the acetylene, that's what we're interested in. The volume's 523 milliliters. What is that in liters? 0.523 liters. R is R. Temperature? (273 plus 23). Is that 296? It was supposed to be 296, yes. 298 is the standard room temperature, 25, and my hand, it's like when you're driving and you end up at school and you were trying to go to the grocery store because you were on autopilot. That's what my hand did just there. I'm pretty sure I did it correctly in the calculator though. No, I didn't. Let's fix that. Two zero 313. Anybody else get that number? Yes, thank you. So that's the moles, and then we need to use the molar mass to calculate the grams. So we've got 2 times carbon plus 2 times hydrogen . 26.036. .529 grams. Any questions? There's like an infinite variety of gas law problems that can be asked. Just so many. Duh, there's another one. If you want to see that one, you can look at last semester's video.